diagnostic tests and interpreting diagnostic tests, we have to introduce you to this concept, because it's not something that you would know intuitively. So, what is a likelihood ratio? Basically, it's a value that we assign to tests, and it's determined by the sensitivity and specificity. We'll go over those again in a few minutes too, just to make sure we're all on the same page as far as sensitivity and specificity. But we use that. Usually they determine a sensitivity and specificity of a test based on a study. Then they know how good are those two values of a test. Then they calculate likelihood ratios. So I'm going to go through this process where we go from a sensitivity and specificity all the way to a likelihood ratio, just so you know how it happens. But the good news for you guys is likelihood ratios are out there. They're everywhere because we use them all the time. People who do practice evidence-based medicine, that is, use them all the time, and they're just there. You could Google likelihood ratio for a rapid strep or a rapid flu or a CT scan or ultrasound, this particular diagnosis, and you would get it. Bam. You don't have to calculate it. So I'm showing you that part so you know where it comes from, but eventually I want to give you guys clues or a way to do this really quick, and you will knock the socks off of your preceptors if you use this in your decision making. You will also right now, and you'll know, because part of this process is coming up with a pre-test probability of disease. And you guys are feeling a little shaky about that right now, right? Because you don't feel like your clinical skills are quite where they should be. And they'll get better. But this knowing how to use likelihood ratios will allow you to have a little more confidence. So it's really important for you to have this now. And later on, as you get more used to using these, you'll become way more comfortable with them, and they'll just be part of what you do, I promise. It will for sure be part of what you do when it comes down to your SPBL, because you'll be required to use this skill when you look at a paper and do a short write-up about it. So you will need this skill very soon, whether you like it or not. And then I hope you see the value in it and you start thinking this way when you look at diagnostic tests. Okay, so first let's go through and let's review sensitivity and specificity. So every diagnostic test we do, usually they're binary, they have a positive and a negative. And I wish they were perfect, right? We wish the tests were perfect, but they're not. Unfortunately, they're not. If they were perfect, we would have two columns. We'd only have this true positive and true negative, right? That's not where we're at. Usually for a test, when we're testing for a specific disease, let's just use the strep screen because we all understand what that looks like. We have either you have strep or you don't. Either you test positive or you don't, right? And we have those patients who do have the disease and test positive. Those are our true positives. But unfortunately, we have patients who have the disease and they test negative. So the test is contrary to what actually exists. And then we have those who don't have the disease. Of those, many people test negative, and that's great. But unfortunately, some people test positive, even though they do not have the disease. This is the reality that we live in. If we don't accept this and incorporate this into our thinking, we will falsely trust tests. We will think they're infallible when they're not. So how do we use this information though? How do we take this all in and allow it to influence what we do? Well, part of that is knowing the values, sensitivity and specificity, but likelihood ratios take this into account for us so that we don't have to take two different numbers and try to make them make sense together. So let's go a little bit further and we'll calculate a sensitivity and specificity here. What do we mean by sensitivity? This is the true positive rate. So another way of thinking about that, because I don't like doing like A plus B over C plus D, and I think it's too abstract. Of the people who have the disease, so of the people in this column right here, how many of those people will test positive? So sensitivity is basically this number in your numerator over all of these people in your denominator, this entire column. That's your rate of true positive, right? It's a rate, so we know there's a numerator and denominator. Your denominator is all those people who have the disease. Specificity is your true negative rate. Of everybody all the patients who do not have the disease, how many of those will test negative? So on your numerator on top, you'll have all the people who do not have the disease who test negative. You'll take that of a rate out of all the people who do not have the disease. So you'll have to include on your denominator all the people who do not have the disease and test positive, plus all the people who do not have the disease and test correctly negative. That's pretty simple, right, conceptually, when you think about it that way and don't try to assign letters to it. Okay, so let's go forward. Let's do a little exercise so that you guys can calculate this out if you need to. Thankfully, this is usually given to you. I just want you to understand it, really understand it, so that when you see these numbers, you'll know what they mean instead of just memorizing things. I just really hate memorizing things for the sake of it. Okay. And plus, this is really fun to be able to do this. Okay, we're going to do a little math. All right, so let's look at a true, and it also gives you an idea how this happens. So this is a study where 200 patients are enrolled because they want to evaluate the accuracy of a new ELISA-based test for influenza. So 200 patients total are involved. 100 patients were diagnosed with influenza by the reference standard of culture. So we accept this as an accurate test, and usually when we're determining sensitivity and specificity, we have to compare it against a gold standard. So that's our gold standard. We know 100 people have influenza based on the gold standard. So I'm going to put down here 100. We know 100 people have influenza. Now, because there's 200 people in the study, and because I made this up, there's also 100 people without influenza, right? Let's keep it simple. So 100 people with influenza, 100 people without, to make up our total 200 patients in the study. Right, nothing too hard so far. So, 80 of the patients with influenza have a positive ELISA-based test. So 80 of the patients of this influenza has a positive test, or true positives, 80 people. As did, but unfortunately, so did 45 of the patients without influenza, right? They also tested positive, but they don't got it. So now we got to take the difference, right? Because they all have to equal 100. This one has to equal 100. So we have here 20, right? And this one is 55. Good job. Okay, so now let's calculate the sensitivity and specificity based on what we have here. So sensitivity is going to be true positives, right, over this whole column, right? So we got that kind of cheated for us, so we know it's 80 over 100, right? This equals 80%, right? 0.80, get real comfortable with that. 80%. Okay, so this one is our true negatives, right? So what is that? Which one is that one? 55, right? 55 over 100, 0.55. Sensitivity, 55. Specificity is 55%. So our sensitivity is a little higher than our specificity. We know this about flus. Unfortunately for us, flu screens are, if they're positive, that's great. It really is great. But if it's negative, it doesn't change a whole lot for us clinically. And that's important for you to realize, right? Because you might assume that one result in a test means just as much as the other. You can't even in a test give as much credence to a positive as you can a negative, based on what the sensitivity and specificity is. So I can really trust a positive, but a negative, not as much, right? It shouldn't guide my thinking as much. I shouldn't walk away from that being like, well, you don't have flu. I'm not entirely sure based on that result. Okay, so let's go back. All right. So, likelihood ratios allow us to shift our suspicion of disease from what we originally think. Because usually when you do a test, and I really want this to be the way you order tests, you're going to go in and you're going to see a patient, and you're going to get their history, you're going to do a physical, and you're going to think to yourself, well, what do I think they have, right? And you're going to come up with your differential, and you're going to think, and so in this case, this guy comes in, I think he has strep, and I'm going to do the test. But in that moment, when I'm doing the physical exam, when I'm getting the HPI, thinking about his contacts, I have to come up with in my mind how likely I think it is he has this, right? Because if I don't think it's likely that he I don't know, there's lots of other diseases he could have. If I don't think it's likely that he has that, I shouldn't do the test, right? I've got to build in my mind a certain probability from the moment I start talking to him before I order tests. It doesn't make sense to just shotgun it and do lots of tests. It's not economical and it's not responsible. So for every test, because there is both a sensitivity and a specificity, and because a test can be negative and positive, there's going to be both a positive likelihood ratio and a negative likelihood ratio. And we define these in terms of their sensitivity and specificity. So I'll show you it later on how you're going to interpret. So you'll be able to look at, when you Google a likelihood ratio and you see both the positive and the negative likelihood ratio, you'll be able to look at that right away and determine, A, is this a test that's worth doing? Is it going to help me make my decision either way? And then B, can I trust it if it's positive? Can I trust it if it's negative? And that's my goal here. So what we should look at here is this right here, your LR positive and your LR negative, and how we calculate those based on sensitivity and specificity. I think we're going to calculate that real quick. Before we go into this, I want to explain why we need these tests to begin with. So all this is based on Bayes' theorem, and Bayes is this mathematician who knows a lot more about this than we ever will. But he said, here's the deal, tests are flawed, they're not perfect. We're not real good at looking at the probability of a test being positive or negative, and then applying that to the general population. Just because if 80% of people with strep are going to test positive, doesn't mean that 80% of the population will test positive, right? Because they don't actually have the risk factors for strep. So we're not good at taking these numbers and putting them in a situation. Also, because the test is not perfect, we have to use context in our interpretation of that test. We all know right off the bat that if we gave a male a pregnancy test and it were positive, we would know that was a false positive, right? Because in the context, it doesn't make sense. Now that's really simple, it's cut and dry, but that also happens in the clinical world too, in other situations that are less easy to see. And so you have to realize that this is a possibility first before you can appropriately assess these tests. And likelihood ratios allow us to do that. So the first thing Bayes tells us is we have to calculate original odds, then we have to look at the evidence, allow that to adjust our thinking one way or the other, and then come up with the new odds, or what we call post-test odds or post-test probabilities. You guys are doing a lot of nodding so far. I applaud you for at least trying. You're really good. Okay, no test is perfect. Let's get some context and then accurately judge the test. So the first test is formulating a pre-test probability. So you'll do this based on your HPI, past medical history, physical exam findings. This is something you're going to find a little daunting at first because you're like, I don't know if I'm really good at this. And now you want me to kind of put a number on it, and that's really tricky. I want you to realize as you go through this that the test is more powerful than you think. It's going to change, and we'll go through an example, and you'll see how it changes that pre-test probability in our minds. And so I don't want you to get too stressed out about that, but you do need to start, because this is something you're going to have to do without thinking about numbers anyway, right? You're going to have to think clinically, what do I think this is? What is it most likely? So if you get in the habit now of saying, do I think it's 20% strep, 50% strep, or 80% strep? It'll allow you to do this in a more methodical way instead of being like, I'm pretty sure it's strep. You know, you need to think to yourself, how much do I think this is strep? How likely is it that it is, based on what I know about this disease, what I know about the pathognomonic clinical and diagnostic findings, as far as physical exam findings. So for the sake of applying likelihood ratios, you could say, honestly, you could say, I think it's 20%, 30%, or 77.5% likely this person has a particular diagnosis. But for the sake of simplicity, and for what you'll notice later on in calculations, I want you guys to assign a 20, 50, or 80% likelihood of disease, probability of disease to these patients. So when you see them, I want you to think in your head, I either think this patient, and it has to be a specific diagnosis, has a 20, 50, or 80% chance of having this diagnosis. In your mind, just make that assessment after you get the whole picture, before you order any tests. Then once you use the likelihood ratio, we're going to apply that, then that will shift that probability up or down. So the first step is getting a pretest probability, and let's compare two patients. So patient 1, and I'm using the throat and strep because you guys have already had HENOT, and I feel like that's fair. So patient 1 is a 15-year-old male who presents with sore throat. On exam, you note lymphadenopathy, erythematous posterior oropharynx, tonsils are edematous with exudates, and he has a fever and headache. Patient number 2, he's also a 15-year-old male, and he presents with sore throat. On exam, you note mildly erythematous posterior oropharynx with cobblestoning. He has boggy, pale nasal turbinates. He has no lymphadenopathy, fever, or headache. Right? So, I don't know, patient number 1, I'm pretty suspicious of strep. Right? He's got fever, headache, lymphadenopathy, exudates in his tonsils. This guy, I need to be thinking about strep. I'm going to go ahead and assign him an 80% pretest probability. In some situations, I may not even do a test on this kiddo. He wants it, I'm going to do it. I think he's 80% likely to have strep. Patient number 2, he doesn't really present like strep, does he? Like, I'm thinking, this sounds like allergies to me, maybe a viral URI, but it doesn't really sound like strep. He doesn't have fever, he doesn't have exudates, he doesn't have lymphadenopathy, he doesn't have headache, blah, blah, blah. It doesn't seem like strep. I'm not really impressed when it comes to strep. So I'm going to assign him a 20% pretest probability of having strep, because I don't really think he has it. And that's fine. So now we've got to run a strep score. But before we do that, let's go ahead and calculate these likelihood ratios. That's fun. So in a study of the ability of rapid antigen strep screens to diagnose strep pharyngitis, 80% of patients with strep pharyngitis had a positive rapid test. 95% of those without strep pharyngitis have a negative test. So it's not terrible. So the sensitivity is 80% and the specificity is 95%. And I'm going to calculate it out based on the, and I'm not going to have you guys do all this. We don't have to go through all of it. But there is our formula. The likelihood ratio is 80 is your sensitivity over, it's really 1 minus specificity, but since these are in percentages, it's 100 minus the 95%, or it could be 1 minus 0.95. Do you know how that works? Anyway, you come up to 18. The likelihood ratio is 18. The positive likelihood ratio is 18. This is a really good likelihood ratio. You'll learn from when I show you a table later on comparing likelihood ratios. This one's pretty good. I like what I'm seeing here so far. The negative likelihood ratio for rapid strep is, here you have your 1 minus sensitivity over your specificity, and you get 0.21. So 0.21, it's all right. It's not terrible. It's not great. You really would prefer it to be 0.1 something, because the lower the number it is for a negative likelihood ratio, the more you can allow it to shift your probability of disease down after a negative test. So it's okay then. It's not terrible. So now we know the pretest probability, right, because we came up with that. We're assigning 20 and 80% to our patients. And now we also know the likelihood ratios. So there's a little hang up here. And the part where I almost was like, never mind, I don't need to know this. But it's really very simple. You can't use likelihood ratios, those numbers, with probabilities. You have to convert probabilities into odds. It's a simple conversion, but people get stressed out about this. In order to multiply your likelihood ratio by something, it has to be in the same values. So you have to convert those 20, 50, and 80% to the ratio. Don't worry about that. Just know that 20, 50, and 80% is always 0.25, 1, and 4. So in your mind, right when you assign 20% chance, think 0.25. When you assign a 50% chance, think 1, and 80% chance, think 4. Because that's what you're going to use to multiply by your likelihood ratio. And that's why I want you to use just those three numbers, because it's really simple to always just remember those numbers. All right, so now let's work through our example. So for patient number 1, that's the guy who had everything pointing towards strep. I thought he had a probability of about 80%. So think 4, right? That's the conversion to a pretest odds. You multiply that by the positive likelihood ratio if he has a positive test. In this scenario, patient 1 had a positive test. So that's 4 times 18, which equals 72. Now I got to convert it back to a probability, right? Because I had odds times likelihood ratio. 72 is something I could look at, but it's really hard for our brains to really interpret odds. We're not very good at that. So let's convert that back into a probability. And whenever you convert back, it's always 72, or whatever your answer is, over the answer plus 1. That's how you convert it back. So 72 over 73 equals 0.98, or 98%. So now my pre-test probability of 80% has shifted all the way to 98%. I am really sure this guy has strep, right? I really maxed out my ability to know this guy has strep. This test has moved it that direction for me. But what if I'm surprised and the test is negative? So I'm going to use the same pre-test probability because I thought it was 80%, so I'm going to think 4, and I'm going to multiply that by the negative likelihood ratio. Because for a negative test, you multiply it by the negative likelihood ratio. That was 0.21, so now it's 0.84. Convert that, so it's 0.84 over 1.84. Whatever the number is, you put that over the denominator of 1 plus that number, and I get 0.45, or 45% likely. So now I've really shifted it down. I was like, sure. I'm like taking it to the bank, sure, 80%. Now I moved it down to below flipping a coin. Right now I'm at 45%. So I'm like, now I'm not so sure. I either got to think about this a little bit more, or think about the way I'm going to treat it. Maybe I'm going to let it go and have him come back. It might be different for me. Or I might do another test. I might decide to do a culture so I can get a 48-hour culture on him, because now I'm just not so sure. All right, so now let's work it out for patient number 2. I have given him a 20% pre-test probability of disease. So in your mind, 20% equals 0.25 when you're going to calculate it out. So 0.25, and the first thing, I think it's going to be negative. So let's assume it is negative, like I think. So the negative likelihood ratio is 0.21. Remember that it was. So we multiply 0.25 times 0.21, and you get 0.05. I convert that back to a post-test probability, and I get 5%. So I went from thinking, well, I'll give him a 20% chance of having this disease. Now I'm down to 5%. I really don't think this person has strep. There is no reason for me to expose him to antibiotics at this point, right? On the other hand, what if I'm surprised and this test is positive? I'm going to use the same pre-test probability, 20%, which equals 0.25 in this situation, multiply that by the positive likelihood ratio of 18, convert it back up. Now I'm up to 81% on this guy. I've gone from a 20% likelihood of disease all the way up to 81% because his test is positive. So now I've got to treat him, right? Obviously. And you were going to. In your mind, if you think about it, you were going to treat a positive strep, right? But now you know mathematically where you need to be thinking about the way you shift your probabilities. So how to interpret likelihood ratios. Here's a table, basically. And you have the likelihood ratios at about a 1. If you look it up, like say you want to Google and find out what the likelihood ratio of a test is for a certain diagnosis. And you can. They're so out there. There's whole books on it. They're available to you really easily. And you see that it's 1. What you should think in your mind is really, I might as well not do this test. It doesn't really change anything. It doesn't change my decision making. It's not going to help me make up my mind. There's no reason to do this. If you get up to 1 or 2, you start to see a little bit of difference. Really, above 4 or 5 to 10, that's where you start to see a moderate change in your probability of disease post-test. So you probably shouldn't even consider a test at the top of your list until it's a 5, until it's above 5. 5 to 10 is good. Above 10, you're looking really great as far as wanting it to change your decision making for a positive test. Now going the other direction on the negative likelihood ratios, the 0.5 to 1, this also is not going to do a whole lot. Now a test might be worthwhile because the positive likelihood ratio is so good, but you should know when you do it If it's negative, it's not going to help me much. If it's positive, it's going to be great. But if it's negative, I'm not going to know a whole lot about that. But you see there, once you get to the 0.1s to 0.2, that's a really good likelihood, a negative likelihood ratio. And it will help you rule something out sufficiently. I want you to see, this is the table, these are actual numbers for a CT scan in appendicitis. Here we have, using a CT scan, likelihood ratios of CT scans and appendicitis for both positive and negative likelihood ratios. So you can see at the top of the list for adults, which is important to note, that it's 18.8. That's really good. If it was positive and they saw something, that could really shift your probability of disease after getting that result. And also, this negative is really good too. So if they don't see anything on a CT scan when you think you have somebody with appendicitis, you can put that to bed. You know, especially if your probability was really low beforehand. You didn't really think it was too high. So ultrasound goes down quite a bit, but it's significant. And this one's actually pretty good. You're negative. Really, this one's a little bit better actually than your positive. But then you get down to some lab tests, and this isn't that helpful. It's not that helpful here. So I don't know if I would really order a C-reactive protein in this. Now, interestingly enough, with children, the ultrasound is actually, the likelihood ratio is actually higher than CT scan, which I didn't know personally. And so with kids especially, you know, based on this table, that this was really great as for a positive result. For a negative result, it's still okay. It's decent. This one's better, but it's still decent. Does that make sense to you guys when you're looking at this? Because I think it will help you when you're trying, especially right now where you're just like, it's all equally unknown to me whenever you look at things. This allows you to look at it and try to prioritize what you're going to do. This is also true. They have these as well, and why I want to introduce this to you now. They have these as well for special tests and physical diagnosis. So we teach you special tests like random things that seem like voodoo magic, right? Whenever we do this and those things also have likelihood ratios associated with them. So whenever you're doing a physical exam, and I consider special tests almost like diagnostic tests because you don't do them for the general population. You only do them when you suspect a certain thing. Whenever you do those things, think to yourself, well, okay, now I'm going to do this. What's the likelihood ratio on that test? How much am I going to let that change my decision making here? And they have that for all sorts of physical exam findings. And that's something that that Professor Fetters will bring up with you. So you'll need to understand what she's saying whenever she talks about those things. So what I want you to take away, guys, is I want you to be able to look at a table, decide which test is worth doing, and then once you get the result, I want you to be able to determine, is that negative worth anything at all? Is that positive worth anything at all? And always, always interpret that within the context of your patient. The other thing is the CT scan. Things like CT scans, especially, you want to look at likelihood ratios because they have a certain level of exposure associated with them. There's a risk to the patient whenever you order these things that are invasive, things that have significant side effects. It's especially important to look at the likelihood ratio in those situations because you need to know if it's even worth it as well. And even if it does have a likelihood, high likelihood ratio, positive likelihood ratio, you still have to consider, is the pre-test probability of disease high enough to warrant doing this? Assigning that pre-test probability, well, if it's really low, it's probably still not worth doing that. Especially if your negative likelihood ratio is too high to make any difference. Yeah, you may not understand that. But anyway, the good news, likelihood ratios are everywhere. You can find them, you can look them up. If you were thinking about something right now, you could Google it, find it, and be able to compare it. You don't have to be calculating it from the sensitivity and specificity, but I want you to know how to do that if you were going to have to, and to know how do we even come up with this crazy stuff anyway. They do lots of studies to determine sensitivity and specificity, and they do meta-analysis on these things that are out there. So likelihood of the accuracy of this is going to depend. It's going to vary between clinicians in some sense because of their ability to come up with a pretest probability, and it also will depend on the numbers that they use to come up with the sensitivity and specificity in the studies involved. So we really would prefer to get all your sensitivities and specificities from meta-analysis from several studies together, or studies that we've deemed to be worth their while from other statistical analysis. But usually, by the time they get to essential diagnosis, Cochrane database, all those things, the sensitivity specificities have been through the mill, so you can trust those. One more thing. Likelihood ratios have never been validated for use in series. What I mean by that is, say you think somebody has like strep, right? And you say, I think they have strep and it was negative. And now my post-test probability goes down to this. Well, there's never been any studies that then said, okay, now that you have this post-test probability, apply a different test and come up with another probability after that. Using them in tandem has never been tested statistically. So it's not something I would encourage you to use. I have no good reason to tell you to do that. So, all right, guys, there's lots of resources out there. The NNT, that's the number needed to treat. It's a group of physicians who put together likelihood ratios for lots of different conditions. They do it by system. It's really interesting website to look at if you were just dying for more information on this. It's out there. Okay.
What if somebody had differential diagnoses? Like, how would it be possible? Can this likelihood ratio put those in a likelihood of trying to figure out what the disease
So
is?
the key to this, the problem is you have to come up with a certain suspect. You know, every time you do a test, there's some tests, those are ones usually that you see. So binary tests, and this is what we're talking about, positive and negatives. By definition, if you use a binary test, you have to have a specific diagnosis in mind when you test it. Do you know what I mean? So if you have a differential, those things you're looking at more value tests like a CBC, which have a lot of values on a continuum. And so that's different, and it's not, there is no likelihood ratio for a CBC in general. There's a likelihood ratio for maybe a high white count with this particular illness. But you'd have to have that in mind when you did it. Do you know what I mean? Okay. All right, guys. Thank you for bearing with me and being so attentive. All right. Have a good day.
I'm contacted by the director of institutional